Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. As you step on inside, we will continue our talk of factoring polynomials. Now, we've done them with the greatest common factor, that's what my last video was about, and using what is called the zero product property when something was factored. We will continue to solve variables using the zero product property as we continue to factor. However, today we are going to be doing a different kind of factoring, not just with the greatest common factor, although we still always seek them, but now factoring quadratic trinomials. Now this stuff can get a little busy and a little it gets fast. If you're really good at it, these are the fun problems to do because you can just go boom 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 and you feel accomplished working them out. But it's something where I'm not going to teach it in full here. I'm going to give you an assumption that you know something on it. If you want to get a little introduction on it, go and check the description section down below. I have a lecture video that gives you a little more insight on what it is that we're doing and how it works with a few examples. But here we're going to get through 20 different examples of these problems here. This first side of this page, if you will, is factoring these 10 right here. And I haven't done these. I crafted these, but then I haven't factored them before. So they're new to me as they are to you. And then the back side will be solving equations that does involve factoring as well. And as you get further down it, they get progressively harder and the different kinds of problems that you have. So again, if you haven't seen this kind of thing before, please check out the description section down below as far as what I'm about to show you, this process, because the more I do it, the faster it gets, but I introduce a few more wrinkles along the way. Okay, factor each completely. Now, the kinds of problems we're going to be factoring is when you have an a value of 1. What does a mean here? We're referring to when you have an ax squared plus bx plus c. This is a quadratic trinomial, where if x was your variable, which is not always true, look at this, here's a p, here's an a, here's an n, oh, there's an x right there. But you know, whatever your variable is, there is this quadratic coefficient, a. And as you can see here, it's a 1, it's a 1, it's a 1, it's a 1, and trust me, it's different when it's not a 1. Now, you are going to see some non-1 coefficients here, but that does mean that there is a greatest common factor of that value, like this 3. That means I can factor out that 3, and that's something that we're going to be mentioning. So it turns into a 1. But when it's 1, we have this idea, and this idea is this. All of these, let me take out the a and just put it right here. This x squared plus bx plus c, all of these can factor into this x plus p times x plus q scenario, where p and q are the sum of p and q give you b, and the product, and the product of p and q give you c. So your constant term is what p and q multiply to make, and your linear coefficient is what p and q add to become. There are reasons behind it. You're going to have to check my little lecture video thing for that if you want to dive more into it, but that's the end goal. So I've been doing some things with my students. These things called diamonds. This is diamond method thing. I'm not going to do this very often here, but just to give you the result, if c on number 1, c is like 66, right? 66 is your constant, and 17 is like your linear coefficient. And this diamond says, hey, your two numbers that multiply to make this and add to make this are going to be what values? And that's what we're asking. What two numbers multiply to make 66? And add to make 17, because those will be the p and q. Those will be the p and q, and when we get those, we'll factor it into this stage here. Enough talk, let's do it. And I'm going to just go slowly through these. I already have an answer in my head, but I'm going to go slowly through these in such a way that if you have trouble figuring out what those numbers are, you want to try and get factors of 66 written down. What do I mean by that? I mean, look at the number 66 and say, let's divide 66 by 1, and you get 66. Let's divide it by 2 and you get 33. Divide it by 3 and you get 22. You can't divide it by 4 or 5. You divide it by 6, you get 11. You can't divide it by 7. You can't divide it by 8. You can't divide it by 9. You can't divide it by 10. You divide by 11 and you get 6. And you can see a repeat here. There's no need to repeat because addition and multiplication are both commutative. You get the same value out. What we're going to say is if this is factorable, and I believe I made all of these factorable, although it's possible to get non-factorable situations. If this is factorable, the products of 66 that we listed out, one of these should be able to add to 17. This is 67, this is 35, this is 25, oh, this is 17 right here. 11 plus 6 is 17, and that's what we wanted. 11 times 6 is 66, 11 plus 6 is 17, so 11 and 6 are our two values. Okay, fair enough. So those are our two values. And that means that is like the p and the q. Those are the two numbers that add to make B and multiply to make C, and P and Q are the result in this factored form. Our goal is to factor. I will be able to do this. This factors into P plus 11 times P plus 6. That's what I'm trying to get as a result. P plus 11 times P plus 6, and I just did. That's my answer. Factoring is the opposite of distributing. We've talked about that with the greatest common factor thing, I'm sure. And the idea is if I FOIL this thing back out, P times P is P squared, P times 6 is 6P, 11 times P is 11P, and 11 times 6 is 66. You combine like terms here, you get P squared plus 17P plus 66. You get that back out. That's just a double check, making sure that it worked. So yeah, the two numbers that multiply to make this and add to make this, you can see why they become those things. 11 times 6 are the last two terms in foiling, and you get that. And these are two like terms that combine by multiplying outside with inside, guaranteed that P is 1. It's a 1P and a 1P. Not that P is 1. P has one coefficient. And 1 times 6 is 6, 1 times 11 is 11, and 6 plus 11 is 17. And that's just what happens. And obviously, look, I went slowly through this problem. I'll speed up as I go, but that's the end result, what we have there in blue. Let's get rid of all the green stuff now. Okay. All right, number 2. Number 2, a squared minus 3a plus 2. Same thing, we have an a squared coefficient of 1. We want to find two numbers that multiply to make 2 and add to make negative 3. Okay, add to make a negative. All right, interesting. We'll get into that. Now, how do you get 2? You can get 2 from doing 2 times 1, and that's it. And 1 times 2, but that's the same thing, right? Hold on, let me get rid of a screen here. 1 second. Okay, so 2 times 1. So the end goal is, listen, we have a positive product of 2. Products can, like 66, that can come from doing a positive number times a positive number, which we did for this one. But 2 can also come from doing a negative number times a negative number, right? Either a positive times a positive, or a negative times a negative. Now, which kind of set am I going to choose? Am I going to do 2 plus 1 or negative 2 minus 1? Well, 3 is negative. Your sum is negative. So if you have a positive product and a negative sum, the end result, guys, is we're dealing with a negative and a negative. Negative minus. Negative 2 minus 1 is negative 3. Because that one works out, it just so happens that negative 2 and negative 1 are our two values that multiply to make 2 and add to make negative 3. And those numbers are our P and Q. So a plus negative 2 is a minus 2. A plus negative 1 is a minus 1, and that's what that thing factors into. I'm not going to double check it, but that's what it is. That's what we get. Let's get that a different color, and let's get different color namesake each and every time there. So that's the idea, guys. That diamond thing that I draw, that's not a requirement of any sort, but I'll do it for the first 4 with you, and then I'll ditch it after that. I can promise you that. All right, number 3. N squared minus 7, n minus 8. Same thing. I have a 1n squared. That means we're going to be able to ask the question here, what two numbers multiply to make negative 8 and add to make negative 7. So this one's interesting because now we have a negative product here. Does that mean I list factors of negative 8? I guess I'm just going to list factors of 8 to start with. We'll talk about how the negative comes into play. Let's divide 8 by 1. We get an 8, and by 2 we get 4, and those are the only unique ones we get out. Now, 8's a negative product this time. A negative product does mean it is a positive times a negative in some way. Positive times a negative. Now, I happen to list the larger numbers on the left and the smaller numbers on the right when we pick and choose which thing goes here, but one of these will be positive and one of these will be negative. Because our sum is negative, that means our larger number will be negative when we test. Does negative 8 plus 1 give us negative 7, or does negative 4 plus 2 give us negative 7, or do neither? It just so happens negative 8 plus 1 gives us negative 7 right here. So it just so happens that negative 8 and 1 are our values. So we choose negative 8 and 1 there, and that means that negative 8 and 1 are the two values that go into place when factored. We're going in that in shorthand notation. Again, go ahead and go to my video to kind of see a little more on why that is and how that ends up to be. I dived into it just a little bit here. But there it is. That's it. Number 4, 1x squared plus 5x minus 84. Once again, what two numbers multiply to make negative 84? This last time I'm going to do the diamond and add to make 5. Now in this case here with negative 84, we got to list our factors of 84 here and kind of see what happens. Let's divide it by 1, 2, 3. Yeah, 3 is 28, I think. 4 should be 21. 5 doesn't work. 6 does. That should be 14. 6 and 14. 7 and 12. Not 8. Not 9. not 10, not 11, and then 12 again. So these are all our factors of 84. There's 6 different pairs of them. We do have a negative product once again, but this time a positive sum. So 1 is negative, 1 is positive. Because the way that I listed them, y'all, the smaller number will be the negative, and the larger will be the positive. This is 83, 40, 25, 17, 8, 5. There it is. 12 minus 7 is 5. So 12 and negative 7 are our 2 factors. 12 and negative 7. We needed to add 2, 5. So that's going to be x plus 12 times x minus 7. Anyway, a lot of the stuff that you see on the side here, guys, this is stuff that can be done mentally, especially the diamond. The diamond is just asking what 2 numbers multiply to make this and add to make this. And I'm not going to do the diamond here on out. Sometimes I'll list factors for myself if I think the numbers are too big, but otherwise I'll tell you them out loud and go through the process with you. Look, I can do these answers on the fly. I can just go, boom, 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 there it is. But I want you to think about what you might have to test when you're doing it. Maybe I'll give you some other strategies. But let's keep moving forward. Let's go to number 5. Number 5, we have 3r squared plus 30r plus 72. Now, we are not going to ask the question. I'll do the diamond for a moment, but I'm going to erase it. We are not going to ask the question what 2 numbers multiply to make 72 and add to make 30. No, this is not the same kind of thing when your a value is not 1. You either need to make it 1, or there is a whole other process that we're going to dive into on a later date. But either make it 1, or you can't do this same exact process in this way. There are other things you could do in the form, but I'm not going to dive into them. I'm more of the mental approach teacher with this, and you're going to have to live with it if you're watching my videos with them. Otherwise, find another video. But what you always want to do with any factoring, guys, the goal of factoring is to get it broken down as much as possible. And the first thing you always want to do is seek common factors. You notice each time I was telling you here, when I said there's a 1n squared, there's a 1x squared and things like that, I was mentioning it because you can't factor anything from a 1 other than 1, which means there is no common factor value with these 3 numbers if it's a 1. This is a 3. There's potential that I can factor a 3 out. In fact, I can. I can factor a 3 out of 3, 30, and 72. All 3 numbers divided by 3. And that's exactly what I'm going to do. When you factor a 3 out, what remains? 3 times what is 3r squared? R squared. 3 times what is 30? 10. And with an r there. And 3 times what is 72? You can go to the calculator, guys, but that's 24. Your end goal there was trying to figure out, could I factor that? I did. So we factored that part, but we're not done because it just so happens that this portion right here is also factorable. Now we go to the question, if I drew the diamond, I'd put a 24 on top and 10 on bottom, and I'd ask what 2 numbers multiply to make 24? And add to make 10. Is it 24 and 1? No, that's 25. As far as adding. 12 plus 2. By the way, I'm listing factors of 24. 24 plus 1? No, 25. 12 plus 2? No, that's 14. 8 plus 3? No, that's 11, but getting closer. 6 plus 4? Ah, there it is. 6 times 4 is 24. 6 plus 4 is 10. So that means that turns into r. Let me put that in blue. That turns into r plus 6 times r plus 4. Now, I shouldn't box this because that 3 is still there. Remember, this is an expression. That means that these 2 expressions need to be equivalent. Don't lose the 3 in the process of doing the factoring. If it helps you, write this to begin with, leave it blank, and then keep trying things until it works. By the way, I've mentioned that there's a possibility that they can give you problems that are not factorable. I'll let you know right now that all these problems are factorable. However, if there was an opportunity where you could find a greatest common factor like this, and you tried to factor this out, and you couldn't factor that, you wouldn't say not factorable because you already factored something. So something's not factorable if the only thing you could factor from the beginning was a positive 1. But, like as in, it doesn't change it. But if I factor out a 3, that's something. It's just you would stop right there. But I could keep going, and I did. That's fully factored. Remember why we're factoring, by the way, guys. Our goal is to be able to solve quadratic equations using the zero product property, and you need to have a product for that to work. Okay, number 6. There is another greatest common factor, and I've mentioned this with my students as well. If in standard form you have a negative leading coefficient, factor it out. Because I'll tell you what, if we were trying to say something like what 2 numbers multiply to make 21 and add to make 4, you're doing it wrong for the same reason you can't say what 2 numbers multiply to make 72 and add to make 30. This negative here defeats the purpose of that because when I just factor this thing out, I can't just say x times x something because that won't give me a negative x squared. And it gets a little trickier with that. So what do? You factor out the negative, specifically a negative 1. But if I factor a negative out of here, I'm left with inside a positive x squared minus a 4x minus a 21. Factoring out just the negative there means that every sign inside changes, and I'm going to leave this negative on the outside for the next stage of this. Just like I said, you could leave the negative on the outside, get this thing written for now, and just kind of work off that. But now we ask what two numbers multiply to make negative 21 and add to make negative 4. And this is a huge difference from this. I'll let you know, there are no two numbers that multiply to make positive 21 and add to make positive 4. But this one is very possible because the negative product, that means one positive, one negative. We're technically going to find a difference to make 4, not a sum. But add to make the negative means one positive, one negative. So here we go, 21. And a negative sum. So is it 1 minus 21? No. Is it 3 minus 7? Yep, 3 minus 7 is. So positive 3 and negative 7 do give us negative 4. So the negatives factored out. We have the x plus 3 times x minus 7. That is the full factorization. So you can tell, guys, we're jumping into some things that have common factors now. After 1 through 4, we're getting common factors, and you got to play with those if they come into play. All right, 4 more on this page here. We have x cubed minus 9x squared plus 14x. Not a quadratic. Not a quadratic. So what do you do when it's not a quadratic? Well, look for greatest common factors before you start asking questions like that. You first ask, is there a greatest common factor? And there is, guys. There is an x that exists in all three terms. Although I can't factor out a number or a negative, I can factor out an x. And what remains in here is x squared minus 9x plus 14. We have one less x power in each of these terms than we had before. And now we have a quadratic trinomial to ask the question, what two numbers multiply to make 14, positive 14, and add to make negative 9? By the way, if it is factorable, that means an x will go inside here, and x will go inside here, something we kind of already know. Positive 14. Negative sum means a negative times a negative. Is it negative 14 minus 1? No. Is it negative 7 minus 2? Yes. Remember, you're choosing your factors of 14 divided by 1, divided by 2. That's what I'm doing with those. Negative 7, negative 2. Very factorable. That's the answer. Don't forget the x on the outside. That was part of the factorization. If I distribute all this stuff, it gets us back to that x cubed stuff. Okay, and number 8 here. Again, there's another x cubed, and it looks like x is a common factor. I sure hope 7's a common factor as well, though, because I need to get it into that 1x squared biz. So yeah, I can divide 63 by 7. I can divide 56 by 7. 7's a common factor. X is a common factor. What remains inside? 7x times x squared gives us 7x cubed. 7x times 9x, 7 times 9, x times x, gives us 63x squared. And 7x times 8 gives us 56x. 7 times 8 and the x. So now we got to say what two numbers multiply to make positive 8 and add to make positive 9. That's 8 and 1. 8 times 1 is 8. 8 plus 1 is 9. My first test, it works out. So 8 and 1, that's my P and Q. X plus 8 times x plus 1. You can see how fast this can get if you know your calculations. I mean, you can use a calculator for those things, but you know, that's kind of what you're doing. All right, 9 and 10 are a little different because we have an x and a y. Does it change things fully? Not really. You know, if I gave a diamond version of this, here's what I want you to recognize, guys. X is really our true core variable, because if you look at this in standard form, remember I talk about x as being a dominant variable. Really think about this instead like this. X squared plus, and normally I wouldn't propose non-alphabetical order, but think of your coefficient as 15y like times an x, and then plus 56y squared. Think of 15y as like your linear coefficient, and 56y squared is your product. If I asked you what two numbers multiply to make 56y squared and add to make 15y, you'd know both of these numbers would have a y in it. And look, I'll tell you right off the bat, guys, I'm not going to go too deep into this. That's 7y and 8y. 7y plus 8y is 15y. 7y times 8y is 56y squared. Why am I telling you all this? Because when we're in standard form, and remember this is proper standard form, when we're in standard form right here and we factor this thing down, we've been mentioning how like this dominant variable, whatever the x goes here. But guess what? The last terms here will have a y in it. So really, this is no different from being x squared plus 15x plus 56. The difference is now there's a y at the end of whatever this answer is. So, you know, to answer this question, that would have been 7 and 8, right? X plus 7 times x plus 8. You know what this one is? This is x plus 7y times x plus 8y. see what happens here when you multiply. Let's distribute this out and let's see if this makes sense with what's happening there. We do x times x, which is x squared. We do x times 8y in alphabetical order. That would be 8xy, because 8 is alphabetically first. 7y times x would be 7xy, and 7y times 8y is 56y squared. You can see where the y's come into play on that, you know? The y's do go in with the linear terms there with the x right there, and then the y squared comes from that y times y. You get x squared plus 15xy plus y squared. So it gets a little in the way, like it bothers you a little bit, but as long as we're in proper standard form, these are all degree 2, but we talk about having the x's being alphabetically first. This really helps you recognize that this is still kind of a constant to us. Don't think of y so much as a variable in the way that x is that same kind of variable, if that makes sense. I shouldn't erase everything. I should just erase the parts that I don't need. So anyway, there's that guy right there, and you know what? Number 10 is very similar because we have the y stuff. However, we also have what appears to be possible common factors. So it looks like I can factor a 3 out of there, which is nice. I need to factor that 3 out. Variable-wise, I got an x here, no x here. I got a y here, and a y here. I have at least one y, and I can factor that y out. So 3 and y can factor. What remains? 3y times what is 3x squared y? 3 times 1 is 3. I factored out the y as well. All that's left is x squared. 3yx squared is 3x squared y. 3y times what is 3xy squared? Once again, 3 times 1 is 3. There's an x I need to place in, and I factored out a y, but y times y is y squared. So there's an xy. Minus 3 times 30, or negative 30, is negative 90, and I factored a y out. Y times y squared is y cubed. So that's what remains inside here. All right, that's what remains inside here. Now, there's still that little trickery as far as the y stuff goes, but you do know this. When it factors, guys, it's going to look something like this, where we know there's going to be an x, a y, an x, and a y. Don't let that y bother you too much. You can almost ignore it and think of it like x squared plus x minus 30, but just kind of, note that we have to insert a y at the end, and the 3y, of course, that's there. Now, this one's a little bit different because, what is x? Well, x is 1x, right? Just like that's 1x squared. So when we're answering this question, we are asking what two numbers multiply to make negative 30 and add to make 1, right? Negative 30 and 1. So negative 30, you got to think of 1 positive, 1 negative. Try 30 minus 1, no. 15 minus 2, no. 10 minus 3, no. 6 minus 5, there it is. Remember, I'm choosing factors of 30, like 6 times 5 is 30. So 6 minus 5, positive 6. Negative 5. And by the way, there are y's there that kind of complete the circuit. So those are final answers there for 9 and 10. We're not going to deal with common factors of greater powers and things with y and stuff on the next page. We're just going to be solving for the variable in and of itself. But that's the first page right there. I hope some of that's making sense. Let's move forward. And I'm going to be faster with the factoring now because of what we just played with there. All right, now we're going to solve each equation by factoring. Now, this is no different from what we did in the greatest common factor stuff when it comes to once we're factored, we solve using the zero product property. So the zero product property, one more time, states that if you multiply values to get 0, if the result is 0 for multiplying two values, or 3 or 7, then any of those numbers would be 0. A equals 0. Or b equals 0. I will also point to you the zero product property link down below as well for some extra stuff on that if you want to see it. But the idea is we set our factors equal to 0, but we have to first factor. We've got to find out, just like right here with the k's, first of all, you got to be set equal to 0. Then if there are any common factors, guys, we're going to factor those out. And then we're going to ask ourselves what two numbers multiply to make this and add to make this. So set it equal to 0, get in standard form, try and find common factors if they exist, and then do the big factoring, like the diamond thing. So we're set equal to 0. We're in standard form. It's a 1k squared, no common factors. Let's ask, what two numbers multiply to make 70 and add to make 17? If you know some of your 70 multiplication, you know that 10 times 7 is 70, and 10 plus 7 is 17. So this factors into k plus 7 times k plus 10. Excuse me. Now remember, we still set it equal to 0, right? our idea is we set this equal to 0, and the reason for factoring was we've created a product. Again, if you saw the greatest common factor video of last, then you know what I'm talking about. I've created a product set equal to 0. That means that we can now solve this properly and say either k plus 7 equals 0 or k plus 10 equals 0. If k plus 7 equals 0, subtract 7 from both sides, k equals negative 7, or subtract 10 from both sides, k equals negative 10. These are the two values that I could substitute into this original equation to make the statement true. I won't do this again, but I'll do it this one time. Let's double check and see that that works. Let's start with negative 7 here. If k equals negative 7, then we do negative 7 quantity squared plus 17 times negative 7 plus 70. And let's see if that equals 0. Negative 7 quantity squared is 49. 17 times negative 7 is negative 119. And plus 70 there. 49 minus 119 is negative 70. Negative 70 plus 70 is 0. 0 equals 0. That checks out. Let's try it with 10. Negative 10. Negative 10 quantity squared plus 17 times negative 10 plus 70 equals 0. Negative 10 quantity squared is 100. This is negative 170 plus 70 equals 0. 100 minus 170 is negative 70, plus 70 is 0. 0 equals 0. That one checks out as well. These are the only two values that work, but they are two values that do work. Just like absolute value equations, quadratics are a parabola. We'll get to graphing these some days, but there's more than one answer most of the time. There can be 2, 1, or 0 answers, all depending on what we're doing. You're going to see mostly 2 answers here. I think 1 or 2 of these might be 1 answer, though. So anyway, negative 7, negative 10, you have to first factor when it's set equal to 0, solve using 0 product property. There are other ways to solve these. We're going to learn them later down the line, but if it's factorable, I recommend you solve by factoring. It's the fastest, it's most seamless, it'll probably make the most sense with respect to what you're doing. All right, number 12. Once again, it is set equal to 0. We're in standard form. No common factor and a 1m squared. Awesome. What two numbers multiply to make positive 36 and add to make negative 15? Well, let's first assume that it's factorable just to get things going, because I'm just going to tell you that they are. Negative numbers. Negative 36 minus 1, no. Negative 18 minus 2, no. Negative 12 minus 3, yeah. Negative 12 minus 3. Negative 12 times negative 3 is positive 36. Negative 12 minus 3 is negative 15. There are our factors. It is factored. We have a product. If this times this equals 0, either this equals 0 or, this equals 0. If m minus 12 equals 0, then m equals 12. Or if m minus 3 equals 0, then m equals 3. Now, I mentioned in the other video, guys, that if you have linear coefficients of 1 in your factors, that means your answer will be the opposite of it. As in, if you have k plus 7, the answer is k equals negative 7. K plus 10, k equals negative 10. You can see how the sign changes there. Minus 12 plus 12, minus 3 plus 3. That is true. That's going to stay true. If I get those, I will skip the step in between, and I'll just give you the solutions. And guess what? All of these will just have a 1 in these, because that comes from this being a 1. So I'm going to be skipping this part here on out, much as I did with the greatest common factor one as we got deeper into it. All right, number 13, set equal to 0, we're in standard form, but this isn't a 1x squared, and we want to see then therefore if there's a common factor here. I'd love to factor out that 2 if possible. Let's go ahead and factor that 2 out, and we're going to get x squared plus 10x plus 25, because 2 times 10 is 20, 2 times 25 is 50. This is set equal to 0. Now, I'll let you know right now, guys, the 2 is not relevant to this problem at this point because it's not a part of our solution set. We need to deal with the x's, not the 2. Because it's not, I could easily divide both sides by 2. I could have done it from the beginning, but you'd have to do it from each term. I prefer asking you to find a common factor before you divide. Either way, you get the same solutions here as you would here. This is a different expression. This would lead you to a different graph, but they still have the same x values for solutions because the 2 doesn't affect what the x is to make these things 0. Only the x affects that, right? Or the rest of the terms in here. That 2 did not. If you multiply 0 by 2, you still get 0, if that makes sense. So anyway, we're still trying to find what two numbers multiply to make 25 and add to make 10. This one's kind of interesting because it's the same number twice. It's 5 and 5. 5 plus 5 is 10. 5 times 5 is 25. So if x plus 5 times x plus 5 equals 0, either x plus 5 equals 0 or x plus 5 equals 0. Either way, remember it's the opposite of this number. That means x equals negative 5. There's only one answer this time because it's the same factor twice. You know, sometimes you'll see this as x plus 5 squared equals 0, and we're actually going to get deeper into these special cases here. These are, it's a perfect square trinomial special case. We'll get into that a couple videos from now. All right, number 14. Negative 5n squared minus 30n minus 40 equals 0. Yeah, set equal to 0, we're in standard form, but I got a negative leading coefficient. I got a 5 instead of a 1. Y'all, you want to get that positive 1 if you can, but especially you must factor that negative out. If you're not factoring that negative out, you're not doing good business for yourself. Get the negative out of there, and all these numbers can divide by 5, so I'm going to factor the 5 out as well. Negative 5 times n squared gives you negative 5n squared. Negative 5 times what is negative 30? That would be a positive 6. And then there's the n. And then negative 5 times positive 8 is negative 40 right there. And there's that factored bit. Hey, you know, I'm going to divide both sides by negative 5 now. I can get that negative 5 out of the way. It is completely irrelevant to the problem. You may choose to keep it or not. I want to remind you guys that when I'm dividing both sides by negative 5 and getting rid of it here, remember, I changed this expression. I literally made it negative 5 times smaller. So you can do this in equations as long as you do it to both sides. I'm doing it in an equation because it's irrelevant to my solutions. On this front page here, I cannot get rid of this 3. I cannot divide both sides by 3. This isn't an expression, or this isn't an equation here. It's an expression. I can't make an expression 3 times smaller. I have to leave it there. That's why I'm really promoting factoring first before you divide, because you can choose to divide later if you'd like to. But make sure that you understand where the factoring comes into play. Anyway, hey, 4 times 2 is 8, 4 plus 2 is 6. So that becomes n plus 4 times n plus 2. I've created my product. Using zero product property, we can therefore then deduce that either n equals negative 4, remember opposite, or n equals negative 2. So those are your two answers there. N plus 4 equals 0, n is negative 4, n plus 2 equals 0, n equals negative 2. All right, number 15, and you're starting to see some different things with these problems here. We're no longer set equal to 0. Well, guess what, guys? It's called the zero product property, and you have to live by that. The zero product property is special in its own way. I know I've spoken in my class about it. I'm sure that my other video does, so check it out if you need to look more. But here's the thing. We need to set it equal to 0. This is set equal to 3. That's no good to us. We need to subtract 3 from both sides here, and I'm going to combine it with a negative 53 because I need this to equal 0. Right? I need it to equal 0. So this is going to say n squared plus n minus 56 equals 0. It's set equal to 0. We're in standard form. We got a 1n squared, no common factors. Let's find out what two numbers multiply to make negative 56 and add to make positive 1. I'll tell you what, the answer, the two numbers are one value apart because something minus something less is 1. Not 56 minus 1, not 28. I already know the answer. But it's not 56 minus 1, not 28 minus 2, not 3, doesn't work. Not 14 minus 4, not, and it's 8 minus 7. It's 8 minus 7, right? 8 times negative 7 is negative 56. 8 minus 7 is 1. So it becomes positive 8, negative 7. So again, I'm going through that process for you so you understand the trial and error. Divide 56 by 1, try it. Divide 56 by 2, 28 and 2, try it. Try those numbers if you don't know immediately, if you can't think of it. Anyway, either n equals negative 8 or n equals 7. You can see how fast this stuff gets once you really make note of the process. You're feeling out what it is that you're doing, and hopefully you understand it along the way. All right, and you know what? So we're getting these problems that aren't set equal to 0. You also notice this about it as well. At the current time that we're at, I couldn't factor a 4 out of these terms here. I couldn't even divide by 4 without getting a fraction, a decimal here, because 121's an odd number. You can't divide an odd number by 4 and get an integer. So, you know, it really is of your benefit to just move that over in the first place. Let's subtract 7 from both sides. Negative 121 minus 7 is negative 128. You'll set that equal to 0. The rest of the stuff comes into play. And now we hope and pray that we can divide all these numbers by 4, that we can factor a 4 out from these. And you know what? You can. You can. You factor a 4 out of here, we get x squared minus 4x, 32. Minus 32 equals 0. I'm going to divide both sides by 4 because, once again, it's irrelevant. Here, let's put it this way. When I say it's irrelevant, check this out. We have a product right here. Do you agree? This is 4 times this. It's like A times B. So if we said, hey guys, if A times B equals 0, then either A equals 0 or B equals 0. Well, guess what? 4 can't equal 0. So that's out, right? We're ignoring that. That's not a part of what's being considered for our solution set. 4 is irrelevant to the problem. I could multiply both sides by 1,000 right here. I could make it 1,000x minus 4,000, 1,000x squared minus 4,000x minus 32,000 equals 1,000 times 0 is 0. And it's still the same answers that you get from it. It's still the same answers that you get for x. Anyway, this, I'm going to save you on the factoring, guys. Negative 32 product, negative 4 sum. That is x minus 8 times x plus 4. Negative 8 times 4 is negative 32. Negative 8 plus 4 is negative 4. Our goal now really is just answering the questions. Either x equals 8 or x equals negative 4 by that flippity floppity flu, the idea of setting those parts equal to 0. You got to know that you're setting those equal to 0 to get to those parts. You got to know we got to set this equal to 0 to even get to that stage. But it's a wasted stage on my end because I recognize the patterns of what's happening. All right, once again, we don't have the set equal to 0, so this negative 8v is like, excuse me, we need to get you over. Furthermore, we don't have a quadratic trinomial, so, you know, as long as we're working on the problems the way that we want to work on them, we got to ensure that we are set up in a way to answer the question being asked, what two numbers multiply to this and add to make this. Notice how I put it in standard form, though. I put the linear term here, so I know specifically that that last term is the product, the middle coefficient right there is the sum, and that's what I'm going for. Anyway, 5 times 3 is 15, 5 plus 3 is 8, so this will become v plus 5 times v plus 3, set equal to 0. Almost done, y'all. Almost done. Running on, I'll probably get done near the 40-minute mark. So either v equals negative 5 or v equals, that's not, okay, or v equals negative 3. Those are your solutions. You can double check some of these still. Try and plug it into the original, though, and see that it works. We'll do it mentally with you on one of them. Negative 5 squared is 25, plus 15 is 40. Negative 8 times negative 5 is 40. Hey, that works. Right, so they should still work with those. All right, number 18. Now I have two terms on this side of the equation. I really want to move them over to this side. You might say, well, let's subtract the 8x squared over. See, I want to keep my x squared term positive, and I don't want to deal more with factoring out the negative later if I don't have to. So I'd rather add the 8x over. I'd rather plus 8x, boom, and subtract the 48 over. My goal is to get 0 on one side of the equation there. Now, I do have it in standard form, but I do have a common factor of 8 that I'd love to pull out of here. 8 divided by 8, you get 1x squared. Divided by 8, you get 1x. Divided by 8, you get negative 6. Remember, this is a 1x right here. What two numbers multiply to make negative 6 and add to make positive 1? Wait for it. Wait for it. 3 and negative 2. Oh, remember, this 8 isn't really needed, right? I mean, you can leave it there. I don't care. But the fact of the matter is 8's not going to equal 0. So either this does or this does. If this does, we're looking at negative 3 for x. If this does, we're looking at 2 for x right there. All right. Excuse me. All right. Two more problems. They look a little more robust, but I promise you they're not. Let's look at one thing at a time, though. We got to get the x squared, the m squareds over, and, we got to combine like terms. We got to set it equal to 0. I'm going to go ahead and I'm going to add 8m squared. Let's do the m squareds first. I'm going to add 8m squared and combine it with the negative 7m squared. Hey, how nice. It turns into a positive 1m squared. I already knew that, bitches. All right, so here we go. Let's add the 7m to both sides here. And now we're going to have negative 20m plus 7m is negative 13m. And let's subtract the 5 over here as well. So we're going to get 0 on this side, and 47 minus 5 is 42. All right, I need two numbers to multiply to make 42 and add to make negative 13. So that both numbers will be negative, right? Positive product, negative sum. Negative 42 minus 1, negative 21 minus 2, negative 14 minus 3. I don't know if there's anything in between. The next one here is negative 7 minus 6. And negative 7 minus 6 is negative 13. So m minus 7 times m minus 6. So once again, guys, we had to get this thing in standard form, get the 1m squared there, set it equal to 0, and now it's factorable. We got it. So either m equals 7 or m equals 6. All right, one more problem here. Won't get it in 40 minutes. That's okay. So here's one of those instances again where we have terms on both sides, and which way do we go? What do we do? I would always err to the side of getting my leading coefficient positive. So because the quadratic term is going to be the leading term here, I want to make this one positive. I think it serves it a lot better if I add the 7n squared to this side so that I can therefore have that as a positive 7n squared. I don't want to have a negative if I don't want to have to deal with it later. And I'll subtract the 8n over, therefore I set this equal to 0 on this side, and then minus 8n with the 78n. And you know what? I want this term next. I want the 168 last. I want this term next. So plus 70n, and then plus 168. Boy, I sure hope that 168 can divide by 7. It can. It becomes 24. So if I factor a 7 out of here, I get n squared plus 10n, 70 divided by 7 is 10, plus 24 equals 0. And I think we've seen this one before. I don't know where, but if you get familiar with these, you can always backtrack and say, where did we find it? I know it's 6 and 4. I just want to show you, like, hey, that's, number, like right here, right? We've seen it before. So 6 and 4, there it is. All right, so let's see. That's going to be 7 times, I'm going to divide the 7. Let's divide the 7 out. And then we get, now remember, dividing the 7 out, I divide 0 by 7, but it's still 0. That's the point of what I'm doing there. Anyway, so this turns into n plus 6 times n plus 4 equals 0. Therefore, either n equals negative 6 or n equals negative 4. Anyway, that is it, guys. There's some nice drill and kill for y'all. That ought to do it for this one, though. The next time you see me do a video on this kind of stuff, you're going to be dealing with the quadratic trinomials where the a value is not necessarily 1. Sure, we might be able to factor some things a little bit lower, but when a is not 1, it gets a little especially tricky. And I know I've done videos on factoring in the past, so I can link you to any of the old videos in the description section down below to help you get a lot of practice with them. But when a is greater than 1, gets a little bit different. It's not just what two numbers multiply to make this and add to make this. We'll do a little bit of anti-distribution. You'll see what I mean with that. Anyway, that ought to do it for this one, guys. This is Mr. Robinson. Thank you so much for watching, and please take care.